But we are
yes, Peter, you can start the Cosmic Zoom video and then live stream.
right now.
Ajit, you can start.
Okay. Good evening, everyone, and welcome to the welcome everyone, and welcome back to the Cosmic Zoom event. Today we have a very exciting talk on the search for habitable worlds, and our speaker is Professor Anand Narayanan from the Indian Institute of Space Science and Technology at Thiruvananthapuram. So before I introduce the speaker, let me remind people that Cosmic Zoom is a virtual exhibition that is curated by the ICTS, and it aims to take visitors through a trip to the cosmos, starting from the smallest scale of fundamental particles, taking all the way to the edges of the observable universe. So if you haven't already taken this trip, I encourage you to visit this website. It is cosmic-zoom.in. And we are also organizing several events, all virtual events associated with this launching of this exhibition. And you can get a full list of these events at cosmic-zoom.in/events. And we're also on social media, various social media platforms, including Facebook, Twitter, and Instagram. So we would appreciate if you followed us and shared us and spread the word. So coming back to today's event, today's speaker is Professor Anand Narayanan, who is going to speak about the search for habitable worlds outside the solar system. It's a very hot and exciting topics, and something that humanity has been curious about a very long time. And Professor Anand Narayanan is a professor, astrophysicist at the Indian Institute of Space Science and Technology in Thiruvananthapuram. His broad research interest is in the understanding of the physical properties of gas associated with galaxies and the intergalactic medium over cosmic time. So he studies the chemical evolution of galaxies over cosmic time. Apart from his professional research, he's very active in the science outreach. He writes very regularly on various aspects of science as well as history. He has produced television shows, award-winning television shows. He has made a documentary on the Trivandrum Observatory, which also received a lot of acclaim. So he's a very versatile person, both as a scientist as well as a science popularizer. So I'm very glad to welcome Professor Anand Narayanan today. Anand, all yours.
Thank you, Ajit. Thanks to ICTS, thanks to Bertie, Anupam, Ghosh, and the entire IT team for inviting me to this very exciting online exhibition, Cosmic Zoom. I'll start sharing my presentation, and just a second. So perhaps someone can tell me whether the screen is visible,
yes.
Whether I'm audible.
Yes.
Yeah. Thank you. Thanks. So good evening, everyone. It's a great pleasure to be able to connect to all of you through this virtual platform, through this wonderfully curated exhibition, online outreach exhibition. What I'm going to talk about today is, as Ajit mentioned, arguably one of the greatest adventures that has been unfolding in astrophysics for the past 25 years or so, which is the discovery of planets beyond the confines of the solar system. So by that, what I mean is planets which are orbiting other stars. So these planets which are orbiting other stars, they are collectively termed as extrasolar planets or exoplanets for short. And research in this field has been getting a lot of traction, has been getting a lot of press and public attention, and rightly so, because, as Ajit mentioned, this topic feeds directly into one of the most profound questions that has occupied the human mind for hundreds of thousands of years, which is the question of whether we are alone in this universe. So this is not a new question. Since the beginning of human history, humankind has looked up at the stars, the vast outer space, and has wondered whether there could be life elsewhere in the universe, whether there could be intelligent life elsewhere in the universe, or whether Earth is the only place in the entire cosmos where conditions are favorable for life to exist. So this question has been occupying human imagination for a very, very long time. And the first step, the first or probably the most crucial step in speculating about life elsewhere is to figure out whether there could be environments outside of Earth that are potentially safe havens for life to evolve into complex forms, the way we see it here on Earth. And as far as we can tell, life as we know it requires a very stable environment. By that, what I mean is possibly a planetary environment. There have been speculations on the possibility of life existing in interstellar space, but if we leave that aside, at least complex life forms, the kind that we are familiar with here on Earth, requires a very stable planetary environment. And therefore, the discovery of extrasolar planets has been crucial in that regard. So in today's presentation, I'm just going to give you a sweeping summary of this field of extrasolar planet research. And I'm going to mostly focus on how astronomers go about detecting planets around other stars. So one of the first things that we all learn in school when we encounter outer space for the very first time is the planets of the solar system. This is our neighborhood. So this is a cartoon that shows the sun and the 8 planets of the solar system. The minor bodies are not shown. So for the most part of the history of astronomy, the only planetary system that humankind had access to was our own solar system. And therefore, all the theories, all the grand ideas and theories about how planets form around stars was based on this one example of our solar system. So if you look at our solar system, there's a beautiful arrangement of planets. If you look at the inner part of the solar system, all the planets are made of rocky, non-volatile materials. By non-volatile, what I mean is material that's very hard to vaporize. So heavy elements, heavy metals, etc. And further out in the outskirts of the solar system is where you have planets which are made of gases and ices which are easily volatile. Okay, so so this, using our solar system as an example, astronomers have come up with very tidy theories of how planets form around stars, but it was a theory based on one example, which is our own solar system. Okay. Now, what you are looking at now is a long exposure photograph of the night sky. In the foreground, the telescope that you see, probably many of you know this. This is the Himalayan Chandra telescope, which is operated by the Indian Institute of Astrophysics in Bengaluru. So the reason why I'm showing this picture is to remind all of us that there are untold number of stars in the sky, and Sun is just one star in possibly 200 billion stars in our galaxy. So there's no reason why, there's no particular reason why only Sun should have planets. So for a very long time, astronomers have been speculating about the possibility of planets being present around other stars. Okay, so there's this question that has been posed for a very long time: is solar system the only planetary system in our universe? If it is not, then how does one go about finding planets beyond the confines of the solar system, beyond the boundaries of the solar system? How does one go about finding planets around other stars? So these planets are now collectively referred to as extrasolar planets or exoplanets. Now, as it turns out, this is a very difficult task. Okay, there are some great barriers. There are some big challenges in directly seeing planets around other stars. So I'll just go about explaining what those challenges are. So here is a artist's impression. Okay, I'm sure many of you have seen this. This is probably an image that we have all grown wary of seeing in social media at some point or the other. This is an artist's impression of the sun and the planets of the solar system drawn to scale. Okay, so the relative sizes are exact. Now, the purpose of showing this slide is to tell you or to remind all of us that planets are incredibly small when compared to a star. If you take the largest planet in the solar system, which is Jupiter, Jupiter is still 10 times smaller than the sun. And a planet like Earth, which you see here almost as a pixel, is about 1/100th the size of the sun. So what that means is you can arrange 100 Earths from one end of the sun to the other. Okay, so that's how big the star is compared to a typical planet. Now you add to this the extra complexity that the stars that we see in the night sky, they are at enormously large distances from us. They are at distances of hundreds to thousands to tens of thousands or even more light years from us. And just to remind you, light year is the distance that light travels in 1 year. Light travels in an incredibly large speed. As an analogy, I would say that in a second, light particle would circumnavigate the Earth about 7 times. So that's how fast light propagates through space. And using that as a distance yardstick, if you were to measure the distances to the stars that we see in the night sky, they are at 100 or 1,000 or tens of thousands of light years away from us, which means light itself would take that many years to reach us. So from those vast distances, even a big star is going to look like a point source. It's going to look like a dot in the sky. Now, it doesn't matter whether you have a large telescope or whether you are looking at the sky with your unaided eye. All the stars that we see in the night sky, even through a telescope, they are going to look like a point source because of the enormous distance that separates us from these stars. Now, so you have a star, which is like a point source, and around it, if there is a planet, then the planet is going to be smaller than a point. So it's going to be first of all difficult to see faint stars, but you can still see them. But planets, since they are incredibly small, they're much smaller than stars, it's going to be more difficult to see them. So that's one of the reasons, one of the barriers. The other is the brightness contrast between a star and a planet. A star, as you know, produces enormous amounts of energy through nuclear fusion process. Planets, in comparison, don't produce that much energy, don't give off that much light. So just to give you an idea, in the visible wavelength region, in the part of the energy range of light that we can see, the contrast in brightness between a star and a planet is 1 billion to 1. So what that means is, if you were to take a telescope and connect the telescope to a CCD camera, and if you were to snap a picture of the night sky, if you were to get 1 billion photons from a star, you'll be getting 1 photon from a planet that is orbiting around that star. By the way, photon is what a light particle is referred to as. So when you get 1 billion photons from a star, you're going to get 1 photon from a planet. Okay? At infrared wavelength, the contrast becomes slightly more better. It's 1 million to 1. Okay? So when you get 1 million photons from the star, you're going to get 1 photon from the planet. So this is essentially the challenge. Okay, you have a star and you have a planet that's much smaller than the star. They are at light years of distance from us, and the star is incredibly bright compared to the planet. And the separation between the star and the planet, as seen in the plane of the sky, is going to be much less than a degree. 1 degree in the plane of the sky. I mean, it's going to be less than 1/3600th of a degree, which is what astronomers refer to as an arc second. So there's a tiny separation between the star and the planet in the plane of the sky, and the star is incredibly bright compared to the planet. So if you just take a picture of the night sky, if you try to directly image extrasolar planets, in the photograph you will see the star, but you will not see the planet. Okay, the common analogy that astronomers use to explain this is, it is like trying to photograph a firefly that is sitting next to a floodlight. So imagine that there is in a stadium, there's a 1000-watt floodlight that is blowing, and right next to it there is an LED. okay, that is emitting light. If you take a picture of it, in the glare of that 1000-watt stadium light, you will not see the LED. Okay? It's the same scenario here. So because of all these things, it's extremely difficult to directly image extrasolar planets. So whatever I just now said, it's there in the form of this small animation. You can watch it. So imagine that this is a star, and it's a planet that's going around the star. The planet is very small compared to the star, and they are at vast distances from us. So being small and dim, these planets are easily lost in the brilliant glare of the giant stars that they orbit. So direct imaging, direct photography of extrasolar planets is a challenge. But that doesn't mean that we cannot find extrasolar planets. As it turns out, there are some very interesting, very efficient, indirect ways of finding planets around other stars, finding extrasolar planets. So what I'm going to do in the remaining part of the presentation is to focus on two of those indirect methods which have been most successful in the discovery of exoplanets. Okay, so one is called the radial velocity method. The other is called the transit method. Now, both these techniques are indirect ways of finding exoplanets. And what I mean by indirect method is we don't directly see the extrasolar planet. Our observation is confined to the star. And based on observations of the star, based on the behavior of the star, and I will tell you in a couple of minutes what the behavior is, based on monitoring the behavior of the star, we infer the presence of a planetary companion to that star. So we don't directly see it, but we look at the evidence that there is a companion that is most likely a planet that's orbiting the star. So hence both these techniques are called indirect methods of finding exoplanets. So we'll start with a radial velocity method. Okay. Now this is a picture which I'm sure is there in most school textbooks. Okay, when you study the concept of center of mass, there will be a picture like this. So here is a wooden plank on which two people are sitting, and if these two people have the same weight, okay, if they weigh the same, then the center of mass, which is that point at which you can balance the weight of these two people, that will be at the center of this wooden plank. Okay, so anyone who has done seesaw, you can easily relate to this. So the center of mass is also sometimes referred to as center of gravity. It's the same as center of mass in a uniform gravitational field. So you can think of the center of mass as a point of balance. Now instead, if in that same seesaw, if you have a person who is much more massive than the other person, then the center of mass or the point of balance is going to be closer to the person who is more massive. Okay. Now we need to borrow this idea to be able to understand what radial velocity method is. Okay. So here is a star, and here is a planet that is revolving around the star. Okay. So generally, we think of planets as going around the star held by the gravitational force of the star on the planet. But gravity is a mutual force. Okay? The star is going to exert a gravitational force on the planet. The planet in turn exerts the same amount of gravitational force on the star. But the reason why the planet appears to be going around the star is because the star is 1,000 times more massive than the planet typically. So that makes the planet look like it is going around the star. But in reality, the star-planet system has a center of mass, which is the point of balance, where the forces of these two objects balance out. So in reality, the planet is actually going around the center of mass of the star-planet system. Okay? The center of mass is sometimes referred to, in the case of a star-planet system, the center of mass is often referred to as barycenter, the point about which the planet is revolving. And the star also, interestingly, does not remain stationary. It also revolves around the center of mass or the barycenter of this system. So that the correct way to think about these two bodies being held together by gravity and revolving around is to think of the planet as revolving around the center of mass or the barycenter, and the star also is revolving around the center of mass. Now, since the star is much more massive than the planet, the barycenter is very close to the star. So the star will be going around in tiny circles, whereas the planet will be going around in big orbits. Okay? So whatever I just said, here is a small visualization of it. Okay, so because of the gravitational pull of the planet on the star does not remain stationary. In fact, it would be moving around the center of mass of the system. That's what is shown in this animation. So this kind of a oscillating motion of the star, okay, in the field of exoplanet studies, this oscillating motion of the star is usually referred to as wobble motion, wobbling, or reflex motion. These are the terms that astronomers usually use to describe this motion of the star and under the influence of the gravitational force, mutual gravitational force between the star and the planet. Now, coming to this, having understood this much, I think we are ready to understand what radial velocity method is. So imagine that this bright object that you're looking at in the slide, imagine that that's a star and this is a planet that is going around the center of mass of the star-planet system. So the star has a companion, that's this planet. Now, the star and the planet will be orbiting the center of mass of the system, okay? And the center of mass is usually very close to the star. Now, in radial velocity method, as I mentioned, it's an indirect method, which means that we don't see the planet. Instead, our observation is confined to the star. So what astronomers do is they'll be randomly monitoring a large number of stars, which means that they'll be using their telescopes to collect light from large number of stars. This light will be sent to a optical instrument called spectrograph. And the purpose of the spectrograph is that it will split the light into its component colors, okay? And it will produce a spectrum. A spectrum is basically when you have, I'm sure many of you have done this experiment in school where we use a prism to split light into its component energies or component colors or component wavelengths. So that's exactly what a spectrograph does. Only thing is it does with a much higher resolution and much higher detail. So the spectrograph, which is connected to the telescope, will record the spectrum of a star. So that spectrum is what is shown in the bottom as colored bands going from violet to red. And you can notice that there are some dark lines that are running through the spectrum. These are absorption lines produced by atoms and ions on the surface of the star. So star is a ball of gas. It has hydrogen, it has helium. It also has trace amounts of heavier elements like magnesium, sodium, calcium, etc. And all these atoms and ions can absorb light as the light emerges from the surface of the star. And so those absorbed lights will appear as dark lines in the spectrum of the star. Now, let's say that we are monitoring the spectrum of a star. And as we are monitoring the spectrum of a star, if the star has a companion planet going around it, then the star will not be stationary. It will be doing this wobble motion. It will be doing this wobbling motion. And when we record the spectrum, if the star is coming towards us, then we will see that the entire spectrum is shifting towards higher energies or shorter wavelengths. So this is called blue shift. Okay? This is Doppler effect of light. And when the star is going away from us, the entire spectrum will be shifted towards lower energies or longer wavelengths, and that's called redshift. That's also Doppler effect. Now, in this particular case, since the star is going around in circles, there will be times when the star will be coming towards us, and there will be times when the star will be going away from us. So what that would result in is, in the spectrum, we will see a periodic blue shift, red shift, blue shift, red shift in the spectrum of the star. This periodic shift is what astronomers use as the observational signal to infer the presence of a companion to that object, even if the companion is not visible. Okay? If a star is perpetually coming towards us, then we would always see a blue shift. And if the star is perpetually moving away from us, we will continuously see a red shift. But if we see a blue shift, red shift, blue shift, red shift in a cyclical manner, then that means that the star is going around in circles, and it can do so only if it is under the influence, gravitational influence of another object. Okay? So this is the essence of radial velocity method. Now, let me just tell you that these wobble velocities, the velocities with which the star will be moving, is usually of the order of a few tens of meters per second. If it's a Jupiter mass planet that is pulling the star gravitationally, And if it's an Earth mass planet that is pulling the star gravitationally, this reflex velocity on the star will be of the order of a few tens of centimeters per second. Okay? So if it's massive planet, it's few tens of meters per second. If it is low mass planet like Earth or Mars, it is centimeters per second. So I want you to comprehend that number, because you are looking at a star that is thousands of light years away, and through measurement, you have to identify whether the star is moving with meter per second or centimeter per second of that magnitude. So this means that this is a very, very fine measurement. It's a very exact, very precise measurement that is needed. Okay, and therefore this entire technique is called high precision radial velocity method, and it is one of the reasons why it took a very long time for astronomers to discover the first extrasolar planet using this technique. So before going into the actual discovery process, I'll just, for those of you who have never seen an observatory, I just want you to, I just would like to take you behind the scenes of what an observatory is and what a spectrograph looks like. Okay, so this is a daytime photograph of the Himalayan Chandra telescope that I showed earlier. The telescope is located in a place called Hanle in Ladakh at an altitude of about 4,500 meters above the sea level. The Indian Institute of Astrophysics in Bangalore operates this telescope remotely using dedicated satellite communication links. So this is the outer dome structure that you're seeing. And if you go inside the dome, you will see a telescope with a mirror. The telescope has a mirror, which is what collects the light. So this is the inside view of the dome. And here you see the telescope here. This entire instrument is the telescope. Okay. And the telescope has a collecting mirror, which has a diameter of about 2 meters. So professional observatories, this is what it looks like. As you can see, there's a lot of mechanical structure to it, and there's a lot of wiring and connections that goes in. So these are very sophisticated instruments, and they are usually located, if they are ground-based observatories, they are located far away from cities and towns, etc., on mountain tops, from where one can get a nearly unobstructed and very clear view of the night sky. Now, I'll just show you the picture. Next, I'll show you a picture of what a spectrograph looks like. But as I mentioned, the kind of measurement that we have to do is very, very fine measurement. So in this particular case of exoplanet studies of using radial velocity, the spectrograph is usually not connected to the telescope, because if you connect it to the telescope, as the telescope vibrates or as the telescope moves, the spectrograph will also shake, and that will degrade the quality of data. So for that purpose, the spectrograph is usually kept in a separate room, and light from the telescope is taken to that spectrograph, which is kept in a separate room with the help of optical fibers. So here is a picture of a spectrograph called HARPS. HARPS stands for High Accuracy Radial Velocity Planet Searcher. It's a spectrograph that has given a large number of exoplanet discoveries, and you can see that the spectrograph is housed in a cylindrical chamber. It's a vacuum vessel, and the reason why it's vacuum is because you don't even need air to pass through it, because if air passes through it, then that affects the refractive index of material through which light is passing, which again degrades the image. So if you were to break open this spectrograph, the cylindrical vessel, you can see inside the optical elements of the spectrograph. And so there's a lot of optical design that goes into it. And I just want to mention that all these discoveries in astronomy is made possible because of the ingenuity and because of the hard work of a large number of engineers who work to build these sophisticated instruments which astronomers use for their scientific purposes. So that was just a peep into behind the scenes of what happens in astronomy. Now we'll come back to radial velocity method, and I'll just go through a little bit of theory in a very simple way, the theory behind this radial velocity method. So imagine that this is an observer and this is a star. Okay? This plus sign here represents the center of mass of the star planet system. And as I mentioned, radial velocity is an indirect method where you don't get to see the planet. So I have only drawn the star here. So this orange thing is the star. And the star is going around the center of mass in circular orbit. And we are looking at it from top. So this is the observer, which means this is where the telescope is. And we are looking at the system from top. And if suppose the star is at this position where it's marked and the star is going around in circles, then its velocity will be pointed towards us. Okay, so it's uniform circular motion, and if you draw a tangent to that point, that will be the direction of velocity. And if you record the spectrum of that star, we will see that the entire lines are blue shifted. They are shifted towards higher energy. Okay. After some time, the star will reach at this position in its orbit. At that point, again, the velocity direction will be tangential to that point in the circular orbit. So this is the direction in which the velocity vector would be. Now, if we are recording the light from that star and sending it to a spectrograph and getting a spectrum of it, we will not see any shift in spectral line. That is because the entire velocity is not directed towards us or away from us. It is directed perpendicular to our line of sight. So this blue shift or red shift will manifest in the spectrum only if the source that is emitting light is coming towards us or going away from us. Okay. In this case, it's exactly at 90 degrees. So you don't see any Doppler shift in the light. After some time, the star reaches here and the velocity vector is once again tangential to that point, and the entire velocity is pointed away from us, so we will see a red shift. After some time, the star is in this position. Once again, the velocity is the same, but we don't get to measure any of that velocity because the velocity is perpendicular to the line of sight. So this repeats. So what this means is that as the star is going around in circles, at some times we'll see blue shift, at some times we won't see any shift, at some other times we'll see a red shift, at some other times we won't see any shift. So there is a cyclical pattern in which the shift in spectral lines will come through. And to understand what would be the functional form of that, all you have to do is just take an arbitrary position of that star. Okay. If this dotted line represents the line of sight to the observer, meaning the line of sight to the telescope, and if this angle, if you define it as theta, which is the angle between the line of sight and the velocity vector, then the component of that velocity, which is directed towards us or away from us, will be v star cos theta. Okay? So if you don't get it, you don't have to worry about it. This is just some essential detail for the sake of students who have studied trigonometry and all these things. I'm just putting this across. So the velocity that we measure is the left-hand side of this equation, and it will change with time. It will change with theta in the following manner. That's what this graph shows. Okay, so along the vertical axis is the velocity that we would measure from the shift in spectral lines, and you can see that the velocity oscillates in a cyclical manner. So this is the observational signal that astronomers use to infer the presence of a companion to a star. Now I will add some more detail to it, and there's a little bit of mathematics, but I'm sure all of you can follow it. So we come back to that same scenario. Here we have the star, and now I am also drawing the planet, even though we cannot see the planet for the purpose of this mathematical understanding. I'm just drawing the planet here. And let's say that the star is separated from the center of mass by a distance a star, and the planet is separated from the center of mass by a distance AP. Okay. And I have drawn circular orbits here. The orbits need not be circular. They can be eccentric also. They can be elliptical also. But let's forget that for the time being. And so the star is going around the center of mass. And what we would measure is v star cos theta. Now, since this is a circular orbit, okay, velocity is distance divided by time. So this v star, we can write as 2 pi a star, which is the circumference of this red circle here. Okay, so that circle has a radius a star. So 2 pi a star by p, where p is the time it takes for the star to go once around the center of mass. Okay, and because it's a circular orbit, it's a constant. Okay, it's uniform circular motion. Okay, Vr is equal to 2 pi a star by p. And what is interesting is that if this is a dynamically stable system, then by the time the star completes one orbit around the center of mass, the planet would also have completed one orbit around the center of mass. Otherwise, it will not be a dynamically stable system. The two objects have to be on opposite sides of the center of mass. So the time it takes for the star to go around the planet is the same, star to go around the center of mass is the same time that it takes for the planet to go around the center of mass. Okay. So VR is equal to 2 pi A star by P cos theta, and VR is this V subscript R is what we measure, and it is in the form of a sinusoid because cosine or sine, that's what the functional form is. Okay. And the semi-amplitude of this will correspond to 2 pi A star by P. Okay. And the duration of this one full cycle will correspond to the period. So that period is the same for the star and the planet. So here is the first piece of information about the exoplanet. Even though we have not seen the exoplanet, if we can construct this, if we can monitor the star for a sufficiently long period of time, we will get a curve like this. And by looking at the duration of one full cycle of this curve, we can find out how long it takes for the planet to go around the center of mass of the system. Okay, so we have the first piece of information about the exoplanet, which we have not seen. Okay. Now VR is an observed quantity. Okay, so the semi-amplitude is an observed quantity. P also we can get from this graph. From that we can find out what is A star. Okay, so 2 pi A star by P is the semi-amplitude. P we know. We can find out what is A star. And just moving along further, if m star is the mass of the star and mp is the mass of the planet, then Kepler's third law says that the square of the period is proportional to cube of the separation between the star and the planet at any given instant of time. Okay, so where this a is the sum of these two distances, and for circular orbits it will be a constant, A star plus AP. Now A star we already know, P we already know, and there are ways to find out what is the mass of a star from the spectrum itself. Stars that are very massive, they have a spectrum of a certain kind. Stars that have intermediate mass, they have a spectrum of a different kind. And stars that are low mass, they have a spectrum of a different kind. So the spectrum itself can be used to estimate what is the mass of the star. P we know from the radial velocity curve. We can find out what is A, because everything else is the constant, and we know A star. From that we can find out AP. Okay, and this is the expression for center of mass. M star A star is equal to MP AP. M star we know, A star we know, AP we know. From this we can find out the mass of the companion. So even though we have not seen the companion, we have arrived at an estimate for the mass of the companion. Now, if that mass comes out to be a very small value, and if we are not able to see that object, then it's most likely a planet. Now, if that mass comes out to be a very large value, and if we are not able to see that object, it could be a black hole, it could be a neutron star, something like that. Okay? So this mass is a crucial discriminator between whether the unseen companion is a large planet or a small planet, or whether it is a really massive object like a black hole or a neutron star. So if it's a black hole or a neutron star, then it's not of interest for exoplanet researchers. But if it's a planet, then you have a detection. So now that was just a quick overview of it. Now, if the orbit is not circular, okay, the planetary or these orbits, dynamically stable orbits, need not be circular. They can also be eccentric orbits. They can also be elliptical orbits. So this animation shows how the radial velocity curve would be if it is non-circular orbits. So the red is the star and the green is the planet, and the cross mark represents the center of mass. So what is the difference between a circular orbit and an eccentric orbit is that the orbital velocity won't be a constant in eccentric orbits, whereas it would be a constant in circular orbits. So if the orbital velocity is not constant, then there will be times when the orbital velocity will be slowly changing, and there will be times when the orbital velocity will be fastly changing. So therefore, our measurement will also mirror this. Our measurement will also, in our measurement also, we will see this, that sometimes the velocity is slowly changing and sometimes it's fastly changing. In other words, the curve will be different from a sinusoid or a cosine curve. So the shape of the curve is used to estimate whether the planet and the star are going around in eccentric orbits or in circular orbits. Okay, so I'll just skip this slide for the sake of time. Now, this method has been extremely efficient. It has yielded a large number of exoplanet discoveries, but the technique has a bias. Okay, this radial velocity technique has a bias, and the bias is the following. Okay, you are looking at the wobble motion of a star, and as I mentioned, if you are looking at a massive, if the star has a massive planet going around it, then the wobble motion would be large and it will be easy to detect this large wobble motion. But if the planet is very small, like Earth, the wobble motion is going to be of the order of centimeters per second, which is very difficult to measure, okay, in terms of shift in spectral lines in the spectrum of a star. So it's easy to therefore find massive planets which are orbiting very close to their star using this radial velocity method. Okay. So that's what is shown here in this animation. So here is a star planet system. If the planet is really massive, then the center of mass will be outside of the star, will be well outside of the star, and the wobble motion amplitude will be larger, okay, which will be easier to measure. So if you are an astronomer and if you do an observational survey of thousands of stars in the sky using radial velocity method with an idea of finding planets around it, then if you look at the data, you will find that most of the exoplanets that you have discovered will be large, massive Jupiter-like planets orbiting very close to their star. And that is because the data is skewed, and the reason is that the observational technique has a bias. So these massive big planets orbiting very close to their stars, these are called hot Jupiters. And we don't have any hot Jupiters in our solar system. In our solar system, all the massive planets are far away from the sun. So just to summarize, the properties of exoplanets that come to us from radial velocity method are: we can estimate what is the mass of the planet, we can find out how long it takes for the planet to go around the star. Does it take 365 days like Earth, or does it take 11 years like Jupiter, or does it take very short amount of time like Mercury or Venus? And we can also find out how far away the planet is from the star, which is very, very important. If the planet is too close to the star, then temperatures are going to be very high, and maybe water in liquid form will not be present. And water, we know, is a precursor for life. So all these things are important when we start to speculate on whether the planet could be habitable or not. The last thing is we can also find out eccentricity of the orbit. Okay. So using this radial velocity method, back in 1995, astronomers detected for the very first time the first extrasolar planet around a sun-like star. This discovery happened around a star called 51 Pegasi, which is approximately 50 light years away from us. It is in the direction of the constellation Pegasus. So from wherever you are in India, this Pegasus would be visible in the months of September, October, November, I think. Okay. So people, they were monitoring thousands of stars. One of those stars was a star called 51 Pegasi. And when they looked at the star, they found out that the star is not stationary. Instead, it is wobbling. And so here is the wobbling signal from that star. Each black data dot that you see is a measurement of the spectrum of that star. And you can see that the spectrum shows that the star is not stationary. Sometimes it is coming towards us, sometimes it is going away from us. So this particular set of data was modeled to detect the first extrasolar planet around that star 51 Pegasi. Okay? And that was the first extrasolar planet ever discovered. This discovery was made in 1995 by two Swiss astronomers, Michel Mayor and his student Didier Queloz. And the planet was called 51 Pegasi b. And Michel Mayor is now a physicist at University of Geneva. And Didier Queloz is now an astronomer at Cavendish Laboratory. So this discovery happened in 1995, and 2019, both of them were awarded the Nobel Prize in Physics for this discovery that happened in 1995. The discovery was important because it kind of jump-started, or it kind of kick-started this entire field of exoplanet studies. After that, there were a slew of exoplanets that were discovered using radial velocity method. So now moving on to the next method, transit method. Okay. Transit method, just to remind you, is also an indirect way of finding extrasolar planets. So here again, we don't directly see the exoplanet, but instead our observation is on the star, and based on a property of that star, we infer based on a behavior of that star, we infer the presence of a planet. So in radial velocity, we were measuring the wobble motion. In transit method, what astronomers do is they constantly monitor the brightness of a star. So in a given patch of sky, they will be monitoring constantly the brightness of thousands of stars. While they are monitoring the brightness, if a planet happens to pass in front of the star, the way we see in this animation, then for that small duration of transit, which could last for a few hours maybe, or a couple of minutes, depending on how far away the planet is from the star. So for that duration of transit, a small amount of light from the star will be blocked by the planet. This will cause the brightness of the planet to dim a little bit. Okay? It's a small dimming of brightness because the planet is very small compared to the star. The planet will not completely block out the light from the star. That would be an eclipse, but that will not happen. Here, since the planet is very small, it's going to block only a tiny amount of the light from the star. And for that duration of transit, when the planet moves in front of us, the brightness of the star will dim. Now, the brightness will again dim when the star goes around when the planet goes around the star and comes back in front of our line of sight. Okay? So repeatedly, if there is a dimming of the light from a star, and if that dimming is of the same magnitude, then that would tell us that this dimming is caused by the passage of an object in front of it. And if it is repeated, then that means that it's not the passage of any random object, it's the passage of an object that is going around the star. Okay, so this is the essence of transit method. Now we can distinguish how big the object is by looking at how deep the dim in brightness is. For example, if a small planet were to move in front of a star, the dim in brightness will be small. And if a big planet were to transit in front of a star, the dip in brightness will be larger. So the relative dip in brightness, how much light gets blocked out, will give us an estimate of how big or how small the planet is that is moving in front of the star. So it depends. The dip in brightness not only depends on the size of the planet, it also depends on the size of the star. So in fact, it depends on the relative ratio of the size of the planet to the star. So by what I mean by that is, if you have a planet going around a star, okay, and if that planet moves in front of the star, it will produce a dip in brightness as shown here. Now, if that same planet is going around a much bigger star, then it's going to block a much smaller amount of light from that star, and therefore the dip in brightness will be smaller. Okay, so the dip in brightness, if we can measure how much the light gets subtracted out when the transit event is happening, that can give us the ratio between the size of the planet to the size of the star. Now remember again that whatever you saw earlier, this is only an animation. We don't get to see, this is an artist's impression. We don't get to see the planet going in front of the star because the star itself is a point source and the planet will be smaller than a point. We don't see it. All we do is we just monitor the brightness, keep track of the brightness, and we look for periodic dips in brightness. Okay. So here is how a light curve, in earlier radial velocity method, we saw a curve and that curve had a sinusoidal form, and that's called the radial velocity curve. In transit method, the curve that we generate is called a light curve. So here is the brightness measurement of a star. You can see that the brightness is constant for most of the time, and suddenly it dips down, and then again it comes back up, and then again it is constant for a time, and suddenly again it comes back down, and then it goes back up, and then again it comes down. So this is a periodic dip, okay? With a definite period, there is a dip that looks exactly the same. So the duration between any two dips will tell us what is the orbital period of the object that is blocking the starlight. And the size of this dip, how deep the dip in brightness is, that will tell us what is the size of the planet, okay? If we know the size of the star, we can find out the size of the planet, because this dip here is that depth is equal to the size of the planet divided by the size of the star square, okay, because it's area that we are talking about. Area is what is getting blocked. So if you know the size of the star, you can calculate the size of the planet. So radial velocity method gave us the mass of the planet. Transit method is giving us the size of the planet. So the two methods put together provides us the complete information about the exoplanet that we are interested in studying. And the separation between two dips will give us the orbital period. Okay. Usually more than one dip, or at least 3 dips, are required before the confirmation of an exoplanet is made. Now, I'll show you the first extrasolar planet that was discovered using transit method. Okay, that is this particular planet called HD 209458b. You don't have to worry about this. This is just a catalog number. HD 209458 is the name of a star. It's the catalog number of a star. So this star was monitored. Its brightness was monitored, and it was found out. It was found that the brightness dips. Okay. Periodically. So the dip in brightness is what you're seeing here. This particular data was taken by the Hubble Space Telescope, and this discovery came 4 years after 51 Pegasi was discovered. And what I would like you to pay attention to is the quantity on the vertical axis. You can see here when no transit is happening, it's 100, and when the transit happens, it's 98.5 in terms of percentage. So that what that means is when the planet moved in front of the star, the light from the star dimmed by 1.5 percentage. Okay, 1.5% is how much the light dimmed. So that means it's a very, very small dip in brightness. And because of that, this transit technique is best done from space-based observatories rather than ground-based observatories. Because ground-based observatories, it's very difficult to achieve this kind of a light sensitivity where you can detect 1% or 2% of dip in brightness. Okay, so usually space-based observing platforms like the Hubble Space Telescope is what is used. I'll just skip this particular slide. I can come back to it if there are any questions related to it. So this transit method also has been extremely efficient in yielding exoplanet detections. Those of you who have been following discoveries in this field would know this. TRAPPIST-1 is a famous transiting exoplanet system. Okay, TRAPPIST-1 is a star. TRAPPIST-1 is the name of a star. TRAPPIST stands for Transiting Planets and Planetesimals Small Telescope. It's a Belgian telescope located in Chile. And TRAPPIST-1 is a star. It's a very cool star. It's not as hot as the sun, and certainly not as hot as some of the other stars in our galaxy. So this TRAPPIST-1 system was observed using transit method using the TRAPPIST telescope. And they found out that this particular star has not 1, not 2, but 7 planets revolving around it. And the transit, the dip in the brightness of the star due to the transit of those 7 planets is what is shown in this graph here. Okay, the star itself is at a distance of about 40 light years or so. And what is interesting about this TRAPPIST-1 system is there are 7 planets. So in terms of the number of planets, it's remarkably similar to solar system. But where it differs from the solar system, where it drastically differs from the solar system is all these 7 planets are very close to the star TRAPPIST-1. Okay? And that is what is shown in this picture. So here is this orange thing. This is an artist drawing of the system. Okay, this is not a real image. This is just an artist impression. So this orange thing is the TRAPPIST-1 star, and all these 7 objects, these are the 7 planets that the TRAPPIST survey discovered. And all of them are very close to the star. In fact, they are so close that we can fit these 7 planets within the orbit of Mercury if these planets were in the solar system. Okay, so they are much closer to the star than Mercury is to the sun. And so this is completely different from the kind of solar system that we have. And this example clearly shows that the exoplanet worlds out there in the vastness of space are vastly different from our own solar system. So in fact, in many cases, this TRAPPIST-1 is compared to Jupiter and its moons. Okay? So this is just to summarize, this transit method gives us the size of the planet. It also gives us a measure of the orbital inclination and orbital time period. Now, these 2 methods that I talked about, radial velocity and transit method, these are indirect ways of finding exoplanets by doing measurements on the star. Now, what would be really interesting is if we can directly see the planet. Now, as I mentioned in the beginning of the presentation, direct imaging of exoplanets is extremely difficult, and in most cases, it's nearly impossible because of the extreme brightness of the star and the small separation between star and planet, etc. Nevertheless, even with existing telescope technology, there are some special circumstances in which a planet can be directly observed. So what I'm going to show, and there is nothing like actually seeing an exoplanet. And so this is called direct imaging. And I'm going to show you a couple of examples where astronomers have actually taken photographs of exoplanets orbiting other stars. So this particular example that I'm showing, this is from November 2008, where a group of astronomers using the famous Keck telescope in the US announced that they have seen direct evidence of planet orbiting the star HR 8799. Okay. So this central region, what you're looking at, which looks like a donut, that is the star, okay? And the light from the star has been subtracted out. That's why it's looking a bit weird here. You can see some residual light after subtraction here. The exoplanets are these four objects, B, C, D, and E. Okay? So you're looking at the photograph. This is not artist impression. This is real data. You're looking at photographs of exoplanets. So these observations were done for a long period of time, nearly 7 years of observations using the Keck telescope at infrared wavelengths using a technique called adaptive optics. So based on those 7 years of observations with the data coming from those 7 years, if you stitch the data together, you can actually see the exoplanets revolving around the star HR 8799. So this is the star here, right in the center. It looks like there is a black circle there because the starlight has been subtracted out. Only if the starlight is subtracted out, we will be able to see the planets. Otherwise, the light from the star will be so bright that the planets will be lost in the glare of the star. So this is B, C, D, E, those four planets. And the bottom, you can see date. And when I play this animation, you will see that the dates are flipping. Okay, the time is flipping, and you will see the planets revolving around the star. Okay, I'll just play it once again. So this 5-second animation is made by data taken over a 7-year time period. Okay, so this is hard work. It's not very easy. Just play it once again. Okay, so this is not the only example. HR 8799 is not the only example. I'll show you one more example. This is a star called Beta Pictoris. And Beta Pictoris is known to harbor one or more planets. So here is a star, and that's the planet that is revolving around the star. So direct images of exoplanets is also now a possibility. As of date, about 100 or so exoplanets have been observed through direct imaging. Okay, just to sum up in the remaining 1 or 2 or 3 minutes, let me just sum up whatever I have to say. So what you're looking at here is a histogram that shows the number of exoplanets that we currently know. It's a cumulative histogram. So what that means is the number of detections in each year is added to the next histogram, so on and so forth. It's also color coded. Okay, the red represents radial velocity method, and the green represents planets that have been detected through transit method, and all the other colors, which are very small, okay, they represent half a dozen other techniques that have been successful in finding exoplanets. So you can see that the graph is mostly dominated by radial velocity method and transit method. And as of now, as of 2021, we know of more than 4,000 extrasolar planets orbiting various stars in our own galaxy. Prior to 1995, the only planetary system that we knew of was our own solar system. And in a short span of 25 years, there's been a tremendous progress in this field. The number of extrasolar planets known to us has swelled beyond the dozens into hundreds and now into a couple of thousand. And this histogram map shows that. And you can see that after about 2014 or so, the green bar is really sticking out, which means that there have been a large number of detections through transit method. And the success of transit method in detecting so many exoplanets is solely attributed to this wonderful observatory, which is no longer operational. This is the Kepler Space Telescope. Kepler Space Telescope was a telescope that was put in space in an Earth-trailing orbit, Earth-trailing heliocentric orbit. The purpose of this telescope was exclusively to find planets orbiting other stars using transit method. So Kepler constantly monitored the brightness of about 150,000 stars in our own galaxy, in a particular region in our galaxy, and it found more than 2,500 exoplanets using transit method. So Kepler really revolutionized the field. If the total number of exoplanets known to us is 4,000, and more than half of it has been discovered by Kepler Space Telescope. Just to tell you how impressive this one mission, this one Kepler Space Telescope has been. Okay, here is a graph. The y-axis shows the mass of planet and the x-axis is orbital time period. So before Kepler, these are the exoplanets that were known to us. Okay, these dashed lines represent the mass of various planets. So anything that is along this line and above it are planets that have mass similar to Jupiter or more massive. Anything that's along this line are planets which have mass similar to Neptune or more massive than Neptune, and this is the Earth line. So you can see that before Kepler, hardly any planet was known which is comparable to the terrestrial planets of the solar system, Venus or Earth. After Kepler, this is how the graph looks. You can see that Kepler has sprinkled this graph with thousands of data points, and what is really interesting is this pileup of data points in and around Earth, which means that Kepler has discovered a large number of Earth mass exoplanets which were not known before Kepler. So the game changer in Kepler has been a game changer in that sense. The number of exoplanets that were known to us increased, Earth-sized exoplanets known to us increased by a 400% after Kepler, and the number of Jupiter-sized planets also increased by a large number. Now I'm just going to skip this biomarker part because it's already 8 o'clock as I see it. So just want to wrap up this presentation by saying that Kepler was a very landmark mission, so to speak, but the mission officially was decommissioned in 2018. But there are a lot of current missions that are ongoing exclusively with the science objective of finding exoplanets, and there are many missions that are planned in the future. One mission that's already up there in the sky, up there in space, trying to find extrasolar planet is this TESS mission. TESS stands for Transiting Exoplanet Survey Satellite. This is a satellite that was launched in April 2018, so it's going to be 3 years now. And unlike Kepler, TESS is an all-sky survey mission, which means that TESS is going to look at a much larger region of the sky than Kepler, and it's going to come up with many more discoveries of exoplanets than Kepler. Okay. Already there are some discoveries that is already out from TESS, but more is coming. And then there is the James Webb Space Telescope, which could potentially get launched this year or maybe next year. And then there's the WFIRST infrared space-based observatory, which is also going to, in future, yield a large number of exoplanet discoveries. So this is my final slide, and this slide is the final takeaway message of this presentation. So even if you were to forget everything that you heard in this presentation, I would like to I would still like you to remember the following thing, which is that when we look at the night sky, we see innumerable number of stars. And if the research in the field of extrasolar planets of the last 25 years, if it has told us anything, then that is this, that every single star that we see in the night sky potentially has one or more planets going around it. Okay, as shown in this animation. This is just an animation. Okay, so it's just a matter of finding these extrasolar planets, which, as we saw, is not easy, but not impossible either. So the moral of the story is that the universe seems to be bursting with planets. In fact, there are probably more planets than stars in our own galaxy, the Milky Way. And this fact has come to us because of hard research in this field of exoplanet studies. And this fact is profoundly important because it enhances the odds of finding Earth-like planets that can potentially be a safe haven for life. A planet similar to Earth with liquid water and a dense atmosphere where the phenomenon of life as we know it is a possibility. And what is even more interesting is that we have only looked at a small part of the galaxy, and already we have found 4,000 exoplanets. So imagine that this is our galaxy. If we could go out of our galaxy and look back into it, our galaxy would look like a spiral galaxy. We are not at the center of the galaxy. We are about 2/3 the distance from the center, about 30,000 light years from the center. So, and all the 4,000 plus exoplanets that have been discovered till date, they have all been found by surveying a small region as shown in here. around the solar system. There's a lot more room to search, okay, in terms of finding planets. And this fact really accentuates the possibility of finding another Earth where life is a possibility. Perhaps, maybe there is a chance that therefore we may not be alone in this universe. We do not know yet, and which is why the future is going to be very, very important. And maybe years from now, some of you, particularly children who are listening to this presentation, you will be at the forefront of making these important discoveries that would open up a whole new perspective on who we are, we here on Earth are, and what our place is in the universe. So coming back to this question of whether we are alone in this universe, which is what drives the public interest in this field, I would just like to end my presentation by quoting Arthur C. Clarke, the famous British science fiction writer. So Arthur C. Clarke once famously said that there are two possibilities. Either there is a cosmic loneliness to our existence, either we are alone in this universe, or perhaps we are not alone. Both are exciting possibilities, and maybe for some of us a bit scary possibility also. Okay, so with that, I will stop the presentation, and I'll be happy to take questions.
Thank you, Professor Anand, for the wonderful talk. And I would request people to type in their questions here. Meanwhile, we'll address the questions which have been submitted already. So, Professor Anand, can you hear me clearly?
Yeah, yes, I can.
Okay, so you can have some water, and we'll start with the questions. So, so the first question is by Shriyans. He's asking, what is the basis of naming an exoplanet? And also, there are similar questions. What do we mean by a planet?
Yeah, so the first one is the easier one to answer. So I'll just start with that. The basis for naming, the nomenclature is very simple. If the star has a name, then the first planet to be discovered around that star will carry a suffix of B. The second planet discovered will carry a suffix of C. The third planet will carry a suffix of D. So for example, if 51 Pegasi is a star, then 51 Pegasi, the first planet to be discovered around 51 Pegasi will be called 51 Pegasi B. The second planet to be discovered around 51 Pegasi will be called 51 Pegasi C, so on and so forth. Okay, so that's the basic way of naming or giving names to these exoplanets. There are no proper names to any of these, because now you have 4,000 plus planets. So if you start giving proper names, you'll soon end up with all sorts of confusion. So at least in catalogs, this is how they are named. And the second question is how to define a planet. Okay, so this is a very interesting topic. Okay, so where do we draw the line between a star and a planet? And usually, I'm going to give a very simple answer, but there's a lot more detail to this. So usually the definition, the differentiation between a star and a planet is, a star is something that can generate energy through nuclear fusion. Whereas a planet, it might generate energy, it might give off energy in the form of light and heat, but that won't be through nuclear fusion. Okay? So this is the distinction between a star and a planet. So in order for nuclear fusion to happen, certain conditions have to be met. For example, the density in the core of that object should be high enough, should be really high enough for nuclear fusion to start, for nuclear fusion to kickstart. And if the object does not meet that mass criteria, then the conditions in the center will never be conducive for nuclear fusion. So this is usually the definition that's used to distinguish between a star and a planet. There are a class of stars called brown dwarfs, which don't undergo nuclear fusion for a very long period of time, but they undergo nuclear fusion for a very short period of time. They also are classified as stars, whereas gaseous objects like a Jupiter, which doesn't look very different from a brown dwarf, is classified as a planet because at no time in its history has it generated energy through nuclear fusion. Neither it will do in future. Okay, so that's the idea.
Thank you, Professor Anand, for the question. Next question is by Junik, and he has a question about moons of the planet. So his question is, after observing and detecting the presence of an extrasolar planet, can we repeat the wobble motion of the planet to detect the presence of exomoons? He further asked, how can a planet and a planet moon companion be classified?
Okay, so using radial velocity method, it's very, very difficult because as I mentioned, even a Earth mass planet is going to induce a wobble motion which has an amplitude of centimeters per second. So you're trying to measure the motion of an object that is as big as the sun down to a precision of centimeters per second. Okay? So usually the uncertainties in radial velocity methods kind of blur out very tiny influences on the star by small objects like moons, etc. So that's through radial velocity, it's not a possibility, but there are some other techniques like gravitational microlensing where one can push the mass limit on the companion. And to be honest, I do not know whether exomoons have been discovered, whether there has been confirmed detections of exomoons around exoplanets. Okay, this is something I'm not able to recollect off the top of my head, but my general answer would be that it's not going to be easy. Okay, even Earth mass planet detections are of much recent happening. So exomoons will be even more challenging. But that does not mean that these exoplanets do not have moons. Moons are in abundance in our solar system. There are dwarf planets, etc. So possibly there are many planets and moons around individual stars that we see in the night sky. But we just end up detecting the most massive ones. That's all. So there's a selection effect there.
Okay. Thank you, Professor Anand. So next question is by Arush. His question is related to the radial velocity method, I think. Can the intensity and frequency of blue shifts and red shifts be used to determine the mass ratio of star to planet?
Mass ratio. So the mass of a star directly comes from the spectrum that we record for that star. So as it turns out, stars that are converting hydrogen into helium in their core, they have a relationship between how bright they are, how luminous they are, and how massive they are. So this correlation between the intrinsic brightness of a star, which is what is referred to as luminosity, and its mass is used to establish the mass of the star. And once we know the mass of the star, we can get the mass of the planet. Suppose you cannot determine the mass of the star. Suppose your observations are not yielding you the mass of the star, or the uncertainties are very large, then you will have to be content with a mass ratio between the star to planet. Okay, I don't know whether that's what the questioner is suggesting, but you will not get an absolute value for the mass of the planet. You will be getting a mass ratio between the mass of the star to the planet. That's about it. Okay. But otherwise, in most cases, mass of the star is determined very well, and therefore the mass of the planet comes from the simple orbital mechanics equations, which I showed in the slides.
Thank you, Professor Anand. I think he was seeking an answer for the shifts are happening in the frequency, but what other information we get from the intensity. So I think you have answered already this. If you would like to add anything to that.
No, so the intensity, what he means is the observed brightness of that object. That depends on how far away the star is. If the star is really far away, the observed brightness is going to be very low. And if the star is closer to us, the brightness could be large. So yeah, that's the only thing. The brightness ratios are more of an observational signal in transit method rather than in radial velocity method. Of course, you need photons to be able to do measurements. So from that point of view, even in radial velocity method, the brightness of the star helps, but it's not a crucial parameter.
Thank you, Professor Anand. So next question is, how have scientists discovered multi-planet systems using the radial velocity method? Won't the period be the addition of cosine waves in this case? So how one would decompose it into the cosine waves of respective planets?
Yeah, excellent question. So I could not go into it because that would take up a lot of time. So multiplanetary systems have been observed through radial velocity method. In fact, one of the star that is closest to the sun, Proxima Centauri, Alpha Centauri system, there multiple planets have been discovered using radial velocity method. So the idea is as follows. If you have multiple planets that are going around the star, each planet will be orbiting the star from a certain distance, which means that each planet is going to take a different time period. Okay, so if you take our own solar system, Mercury takes 88 days to go once around the sun. Venus takes 250 days to go once around the sun. Earth takes 365 days. And Jupiter takes 11 years. Okay, so now what happens is, when we measure the radial velocity, suppose we are an alien astronomer and we are looking at our sun from a far distance and we are trying to measure this radial velocity, what we would see is that the sun is exhibiting a wobble motion with a period of 11 years. Within that 11 years, we will see that there is a subsequent periodicity of 365 days. Within that, we will see that there is a period of 250 days, and within that, we will see a period of 88 days. So it's like harmonics, okay? So it's not strictly harmonics, but I'm just giving a loose analogy here. So it's like you fit, so when they get the radial velocity data, they try to look for the dominant periodicity, and then they fit it with a model, and they subtract the model with the data, and they look at the residual, and they try to look at the residual and see whether there is any periodicity in the residual. And if there is a periodicity in the residual, they'll fit that, and then they'll subtract again and look at the residual of the residual. So this is an iterative process, and often, as you can very well imagine, the massive planets jump out from the data very well. It's the low mass planets that test the limit of the data and the test the limit of our analysis. Okay, and so, but it is not impossible. Periodogram analysis, for those of you who do periodogram analysis is what people do to do this. A Lorentz-Cargill periodogram is a common tool that's used. So this is the way multiplanetary systems are discovered. It's hard, but it's not impossible. Okay.
Thank you, Professor Anand, for the question. The answer. And we have, I'll club 2 or 3 questions together in save time. So there's one question which asks, is there a limit to the size of the mass of the planet with respect to the star which it is orbiting? That's part 1 of the question. And then there are other questions which are asking, will more planets make the star wobble more? And will that contribute to making the measurement difficult? What is the maximum number of planets observed in a star-planet system? I've clubbed 2, 3 questions together.
Yeah. Okay, so first is there a limit to the mass of a planet? So I presume what the questioner means by that is a theoretical limit. Okay, is there a theoretical limit on how small a planet can be? And I don't think there is any theoretical limit. Only thing is that International Astronomical Union has now come up with an official definition of what qualifies as a planet and what doesn't qualify as a planet. So for example, there are many dwarf planets in our solar system, which do not fit into the classical definition of what a planet is, but that's, human gain. Okay, that doesn't mean that those objects are not there, they're still there. So it's just a issue with naming. So from that point of view, I don't think there is any lower limit on how small a planet can be. There's an upper limit on how big a planet can be, and that is set by the mass limit beyond which nuclear fusion can happen in the core of that object, and thereby it will become a star. Okay, usually the objects that touch the upper mass limit will be gaseous planets. The reason is very simple. There will not be a Jupiter mass Earth-like planet. What I mean is a rocky Jupiter mass planet is impossible because the gas cloud from which stars and planets form does not have that much heavy elements like aluminum, iron, magnesium, silicon, sulfur, etc. to form rocky objects that are that big as Jupiter or Saturn. The gas clouds from which solar systems or planetary systems form is mostly made of light elements like hydrogen, helium, etc. So the inventory from which planetary systems form do not have enough material to form big rocky planets. So if the planet is big, it should be gaseous. It ought to be gaseous. And if it is gaseous, then the core of it could also be a gas that is highly compressed, where nuclear fusion can happen, and therefore that sets a limit. Objects which are more massive than 13 times, 13 times the mass of Jupiter, usually can have nuclear fusion for a very brief period of time in their core, and therefore that's the upper mass limit. The second question was, can more planets make a star wobble more? Yes, they can make a star wobble more, and it will make life difficult for astronomers who are trying to find exoplanets around them. So, but the technique is quite sophisticated. So as I mentioned, astronomers have found exoplanets around Alpha Centauri, Proxima Centauri system, which is a stellar triplet system. So it's not just planets around one star. Okay, there are planets around multiple star systems which they are finding. So you have to subtract out the wobble due to the gravitational pull between the individual stars before you can actually go and find the wobble from planets. So the limits are being pushed. Okay, in that case. The last question was, what is the maximum number of planets that have been found around a star? I do not know for absolute certainty what it is, but I think TRAPPIST-1 is a good example of a large number of planets around a star, 7 planets. Okay. So just to give you a feel for it, if you are an alien astronomer looking at our solar system from some far distant corner of our galaxy, using the same sensitivity of instruments that we have, then you will arrive at a conclusion that the sun has 1 or 2 planets around it. Okay, and that's because our observational sensitivity, we will not find Mercury, Venus, Earth, or Mars, or any of the dwarf planets, or the comets, or the asteroids. So there's probably a lot more lurking in each of these planetary systems than what our current observations yield us. Okay, so that's what I have to say.
Thank you, Professor. Thank you for the example. Very interesting example of Earth. The solar system. Yeah. So there's an interesting question by Vivek Reddy. He is asking, can a periodically pulsating standalone star produce these signals for radial velocities?
Yeah. So periodically pulsating stars. Is the person referring to pulsars, or there are a class of stars called pulsars which are periodically pulsating? Or
no, he has not mentioned any name of a star. He is saying this: is it possible that there is no companion planet and you are still seeing those signals?
Yeah. So the short and easy answer that I can give is that the people who do this, okay, they scrutinize all these things to death. Okay, they look for all kinds of intrinsic variability of the star before they flag the detection as a potential exoplanet. Okay, for example, if you're talking about transit method, there we are measuring the brightness variation. Now there are stars whose brightnesses vary intrinsically, even if there is no planet. There are stars that grow in brightness and that fade in brightness periodically. So how do you disentangle that from a planet going around it? So there are the observational signature of the pulsations of stars resulting in their brightness variation is different from the observational signal that we get when a planet transits in front of a star. So there are telltale signatures that people look for, and that's the short answer that I can give. So every claim of an exoplanet detection is looked at with a lot of care and with a lot of skepticism before a potential claim for an exoplanet is actually made.
Thank you, Professor Anand. So the next question is by Sachidanand, and he wants to know, won't matter between the line of observation affect the light which directly comes from the star? So how do we account for or infer, how do we account for such errors? And next question is, similarly, other planets would bend the light because of the general relativity. So are these errors accounted for, or do they happen? Yeah.
Yeah, so in the extinction or the dimming of light because of interstellar matter that is between us and the star that we are observing, that interstellar extinction is taken into account. In radial velocity method, it's not a big issue because we are measuring kinematics. We are not measuring brightness. So even if the star appears a bit dim, it's okay. The only problem is that it will affect your signal to noise. The star will be fainter than what it actually is. So because of this interstellar extinction and the distance to it, the distance to the star. But for transit method, this could be a problem, but it's not a problem. It's not so much of a problem because the interstellar extinction is going to uniformly dim the brightness of a star. Okay, but whereas in transit, the signal that you're looking at is brightening and fading and brightening and fading and brightening and fading. So it's a different kind of signal that you're looking at. So, but interstellar extinction is also taken into account. The other question was, I'm sorry, what was the other question?
The question was that, I'll just read it out. That Einstein's general relativity says that light bends when passing by next to a big matter in space. When we observe light, there will be errors due to bending, and how do researchers account for it?
Yeah, so in fact, interestingly enough, this bending of light as it passes through a curvature in space, this is used as a tool for finding planets. The technique is called gravitational micro lensing. Okay, but it's a really bizarre technique because you don't see the star, you don't see the planet. So you end up discovering a planet that you don't see around a star that you don't see by observing a background star. So gravitational microlensing, there have been only a handful of such detections. Whether this bending of space and bending of starlight will affect radial velocity or transit method, highly unlikely. The probability of two stars being bang on top of each other is very, very small, but these micro lensing signals are also looked at, okay, before they are also corrected for, but I don't know exactly to what extent they affect the measurements. If they will add a systematic uncertainty to the measurement, I do not know that.
Thank you, Professor Anand. So I think I focused on the questions which were directly related to the methods. Now there are many questions which are asking, what are the methods?
Can we like have questions for like next 3-4 minutes and then wrap up?
Absolutely. Okay. So 8:30 we stop sharp.
Okay, great. Yeah.
I have already addressed questions related to the talk. Only there are several questions which are asking what are the methods by which we get to know if the planet has atmosphere or if it hosts water. There are many questions asked.
Yeah, so thanks for asking this because this is the part of the talk which I left out. Okay, so currently in exoplanet research, the frontier areas of exoplanet research, what is being done is not beyond the detection of exoplanets. Astronomers are also trying to address this question of whether this planet potentially has an atmosphere around it. And if it has an atmosphere, what is the chemical composition of that atmosphere? Now, the way atmosphere is detected is when a planet transits in front of the star, okay, the light from the star gets blocked out by the planet's solid surface. But if it has a wispy atmosphere around it, then some of that light is going to pass through that wispy atmosphere. So if in that atmosphere there is H2O or there is O3 or there is O2 or there is methane, then those molecules will selectively absorb photons which are coming from the star, and they will produce absorption bands in the spectrum of that star. Now the interesting thing is, one may ask, okay, those absorption lines could be present in the star itself. So the interesting thing is, those absorption lines will vanish once the transit is over. Okay, the lines will manifest only when the planet comes in front of the star, when the light from the star passes through the planet's atmosphere. Once the transit is over, those lines will vanish. They will again appear when the transit happens. Okay, so this is called transmission spectroscopy, and this is one of 3 techniques that are used for finding or detecting atmospheres of exoplanets. Now, what is the big deal in detecting atmospheres of exoplanets? Well, there is an argument that the chemical composition of the atmosphere of an exoplanet can tell us whether the planet has a biomass. What I mean by that is whether the planet is sustaining life. And the classic example to understand this is comparative study between Venus, Earth, and Mars. So if you take Venus, Earth, and Mars, all three planets have atmosphere. Only thing is, in the case of Mars, it's a very, very thin atmosphere because Mars is a low mass planet, so it's losing its atmosphere, but all three have atmospheres. Venus and Mars, the dominant molecule in the atmosphere is CO2. Whereas if you look at Earth, there is CO2, okay, 20% is CO2, so not 20%, very small amount is CO2, much less than 20% is CO2. But in addition to CO2, we also have O2, we also have O3, we also have H2O. So there's a lot of oxygen and related molecules in the Earth's atmosphere. Now, most of you would know that the abundance of oxygen, the Earth's atmosphere became oxygen rich after the first life forms originated on Earth. Photosynthetic algae, cyanobacteria, etc., which did metabolism, and the byproduct of metabolism was oxygen. So they took in carbon dioxide. This is anaerobic metabolism. So they took in carbon dioxide and gave away oxygen into the atmosphere. So the oxygen levels in the Earth's atmosphere increased after the first life forms originated. Now, and the life forms on Earth is what sustains oxygen in the atmosphere at the 20% level, at 1 part in 5 level. Now, if all life on Earth were to vanish today, then the entire oxygen in the Earth's atmosphere and all the molecules associated with it will go away in a manner of few million years. All the oxygen will start corroding or rusting the minerals that are present on the Earth's surface. Most of the oxygen, etc., will dissolve in the Earth's oceans. So the simultaneous presence of gases like CO2 and O2 and O3 and H2O is an indication that there is a possible biomass to that planet. Okay, and so if you are an alien astronomer looking at the inner planets of the solar system, you will clearly see that the Earth's atmosphere is different in chemical composition compared to its neighboring planets, Mars and Venus. And the reason for that is Earth is sustaining life. So these molecules are called biomarkers, and currently in the field of exoplanet research, astronomers are pushing the envelope on trying to detect these biomarkers on exoplanet atmospheres. And that's going to be a very interesting topic in the coming years as these space observatories provide better data. Okay, so this is the idea. And yeah, thanks for asking it, because this is something which I wanted to cover.
Thank you, Professor Anand, for the wonderful talk and answering so many questions. And there are many comments in the chat that they would like to hear a talk on biosignatures. Maybe we can ask you for the next time. Yeah. And I really like the perspective of alien astronomer. Fantastic. Thank you once again. With this, I will ask Bertie to take over. And thank you so much, Professor Anand.
Thank you, Anupam. Thanks.
Thank you, Professor Anand. That was excellent, exciting, and very engaging. And a huge shout out to everybody who's joined us, all the participants on both Zoom and on YouTube. Thank you for being part of this. Thank you for the excellent questions. We have more talks coming up. Tomorrow we're taking a break, but back again on 13th of April, Shashi Tatapalli, who's a brilliant physicist biologist at NCBS, will be talking about metabolism and probing life's engine at 7 p.m., followed by Professor Rama Govindarajan, who is a professor of fluid dynamics at ICTS. She'll be talking to us about cloudy and turbulent days and the wait for rain. Apart from this, also every single day we have mediator guided tours of the website cosmic-zoom.in. This is for people of all ages, of all academic or research or even laymen. You will get a fun, engaging tour done by mediators. You can log in at any day, on any day at 10:30 a.m. All the details are on all platforms, social media platforms. You're there on Twitter, Instagram, and Facebook. And I would like to especially say thanks to those people who have joined us from other parts of the world, from the University of Bern, for example. Thank you, sir, for joining us. And thank you for sharing the love that we have for science. The video of this talk will be available. We will edit it a bit and then put it back online at the website. And all that remains for me to say right now is a huge shout out and thanks to Professor Anand Narayanan for taking time off and doing this amazingly engaging talk. Thank you, sir. It's been a lovely evening, and We hope that within our lifetime we find an exoplanet that we can all look forward to going to. I remember reading about this in science fiction, and I love the fact that you were able to talk about Arthur C. Clarke. And well, I'm looking forward to science fiction becoming reality soon. Anyway, thank you so much to everybody who's attended. This is me, Bertie, actually saying thank you. Have a good evening and good night. We shall catch you another day. Please follow us on Cosmic Zoom on all social media. And that brings an end to this session. Thank you, one and all. AV team, you can close the stream. Bye, everyone.
Okay,
Live long and prosper.